All right, our new unit this time is all about the gas laws. And we're going to study how gases behave and what happens when you heat them up and cool them down and all that kind of good stuff. So here we go. First of all, we're going to talk about the kinetic theory. There are 5 main things here that make up this theory. One is particles of matter are always in motion. Even if they're in a solid, they're still moving. The volume of individual particles is approximately 0. And then when these particles are always moving, the collision of particles cause pressure when they hit the container. So we're going to assume that we know this to be true, okay? And then particles exert no forces on each other, and the average kinetic energy is approximately equal to the Kelvin temperature of gases. And remember, kinetic energy is the energy of motion. So the more motion it has, the higher the temperature is going to be. All right, the first guy to ever measure atmospheric pressure, or the first one to create a device for it, was this lovely man right here. Whoops. I used the wrong tool. Sorry, guys. This lovely man. I'm trying to get rid of that. There we go. Okay. This lovely man. Isn't he beautiful? Yeah, no. So, anyway. His name is Evangelista Torricelli. And this little name right here, Tor, is going to be very important here in a minute when we talk about units for pressure. Okay, so this is in the 17th century, so in the 1600s. This device that he used was called a barometer, and it came from these words. Baro means weight, and meter means measure. So you're kind of measuring the weight or pressure. Okay, and this is kind of what the early barometer looked like. It was not very sophisticated, as you can tell, and basically what he found was that the normal pressure due to the atmosphere at sea level can support a column of mercury that is 760 millimeters high. So right here would be 760 millimeters of mercury because of the pressure coming down here from the atmosphere. Okay? And this is what a modern day barometer looks like. Slightly more high tech. Okay, when we're talking about pressure, there are different units, and they kind of can be confusing, but this is what we're going to talk about. And this is the pressure that's caused by the collisions of molecules colliding with the wall of the container. Okay? The pressure units are equal to the force divided by the unit area. Okay? And remember, force is measured in newtons. And measurement for area, which would be like a distance, would be meters squared. Because you have meters times meters. Okay? So the SI unit, which is the standard used unit, is the Newton divided by meter squared, which is commonly called 1 Pascal. Okay? And then 1 standard atmosphere, which is ATM, is 101.3 kilopascals. So a little bit more there. And 1 standard atmosphere, 1 ATM, is also that 760 millimeters of mercury. Remember in that first old-timey barometer, it was 760 millimeters high in that mercury, which is also equal to 760 torr. Remember that guy's name was Evangelista Torricelli or something like that? And this is where the torr comes from. That we'll see that later. And this is just another graphic showing you the different pressures, their units, what it's called, the symbol for it, and then its relationship and how it kind of fits into the picture of pressure. So if you want to pause this and make sure you get it all filled in there. Okay, and in order to plug into some of the gas law formulas, you have to convert temperature to Kelvin, but you have to know what Kelvin is. So basically, as you cool a gas, you're going to decrease the volume of it. As something gets cooler, it just kind of shrinks down, is what we say. The volume decreases. Every 1 degree Celsius, it decreases by 1/273rd, which is where we get this number from for the Kelvin conversion. Okay, negative 273 is absolute zero. Negative 273 Celsius, which is 0 on the Kelvin scale, because if you look here, 0 minus 273 gives you 273, negative 273. Or vice versa, if you're going to Kelvin, negative 273 plus 273 equals 0. So this absolute 0, this is where all motion ceases. It has yet to happen that we can reach this absolute 0. Scientists have tried. Okay, and then we talked about standard temperature and pressure. Okay, we've got 0 degrees Celsius or 273 Kelvin, 1 atmosphere for pressure, 760 millimeters of mercury, or 101.3 kilopascals. And this is also called torr here. Okay, there's 5 things that gases do, or you should know about them. They expand to fill their container, and they are fluid, which means they can flow easily. They have low density. They are compressible, meaning you can squeeze them down into a smaller space or volume. And they effuse and diffuse. All right, now we're on to the first law. And we have another lovely young man over here who was also around in the 17th century or the 1600s. His name is Robert Boyle. He was Irish and he was a chemist. And his law states that the volume of a given amount of gas held at a constant temperature varies inversely with the pressure. This is a key word right here. Whoops. Inversely with the pressure. As pressure increases, volume decreases. And we have this little formula right here for Boyle's law, and it's pretty standard. From what we've seen before. Basically, the key thing for you to understand is that if you look here at the graph, what happens as pressure is increasing? Volume is decreasing in this direction. Okay? So when pressure goes down, what do we see volume does? If it goes down this way, volume goes up. If pressure goes up, volume goes down. They are inversely related. That's what inversely means. As one goes up, the other goes down. And here is a practice problem. And you can look at how it's set up here. Or I'm going to squeeze this down and I'm going to work it right above here because I think it's slightly confusing the way it is there. So let's use a green color here. All right, it's asking you to convert from 825 torr to kilopascals. So it's kind of like stoic a little bit. We've got 825 torr and we want to go to kilopascals. So what has to go on the bottom? Torr. And what has to go on the top? The thing we're looking for, kilopascals. So we use our conversion, which is right down here for you. In 101.3 kilopascals, there are 760 torr, which is also equal to 1 ATM, if you remember. And remember, this is also called mmHg. Okay, so then you just multiply 825 times 101.3 divided by 760, and that should give you 109.96 kilopascals. And if you pay attention to significant figures, we want our answer to have 3. So it should be rounded up to 110. All right. Now let's look at the bottom problem. It's another one using Boyle's law, and it's not just a conversion. It says solve the following. The volume of oxygen at 120, hang on just a second, let me get a different color here. The volume of oxygen at 120 kilopascals is 3.2 liters. So we've got our first pressure, P1, and our first volume, V1. And it's asking you for the volume, so we're looking for V2 at our P2 of 101.3 kilopascals. So we're going to plug into this formula. So we have P1, which is 120, times V1, which is 3.20, equals P2 is 101.3 times V2. So in order to get V2 by itself, we have to divide both sides by 101.3. And we should get for V2 3.79. And that's good for our sig figs and our units as liters since it's volume. Okay guys, we're getting close. Bear with me. We're almost done. This is the last law we're going to talk about on this video. And this is Charles' law. His name is Jacques Charles. And he's a little later than Boyle. He was in the late 18th century, and he's a French physicist. And he found that the volume of a gas varies directly with its absolute temperature. And so what he found was that as temperature increases, volume increases. So these are what we say is directly related. When one goes up, the other goes up. When one goes down, the other goes down. And so on and so forth. Unlike Boyle's law, which were inversely related, they were opposite. Okay? And here's our formula. V1 divided by T1 equals V2 divided by T2. And we have an example here. It says solve the following. The volume of a gas at 40 degrees Celsius is 4.5 liters. Find the volume of the gas, that's our unknown, at 80 degrees Celsius. The first thing we have to do when we plug into these formulas is change Celsius to Kelvin. And if you remember, those conversions were Kelvin equals Celsius plus 273. So we have to add 273 to both of these. So 40 plus 273 is 313, and 80 plus 273 is 353. Now we can plug into our Charles' law formula. V1 is 4.5, T1 is the 313 we found here, V2 is the unknown, and 353 Kelvin is our T2 from here. Now, to do the math, you have to multiply 353 on both sides. So we would have 353 times 4.5 divided by 313, and we get approximately 9 liters. And we should go ahead and round that to write it as 9.0 so that we keep our sig figs in line. And that, my friends, is the last slide for this video. Hope you enjoyed it, and I will see you on the next one. Bye-bye.